In this video, I would like to talk about user-defined detectors in RayJack ONE, a very flexible and versatile tool for non-standard analysis of optical systems. Let me go here to the system I want to show. It's a time-of-flight sensor. So a laser illuminates a scene. Light gets scattered from objects into a receiver optic, which is here modeled as an idealized lens and a pixel sensor in the focal plane with a focal length f. Now, each pixel of the sensor measures the time of flight of the light sent by the laser, getting back reflected, and then finally hitting the sensor. And the optical path length is simply the time times the speed of light. Now, the goal of such time-of-flight sensors is to reconstruct a three-dimensional scene through a point cloud. And first of all, we need to know the distance of an object from the lens. And since the ray has to do a double pass, and we have here this extra piece, the focal distance, we find that the distance to the object is the optical path length minus focal length over 2. This is only approximate, and in real life it may be more complicated, of course. And but for our purposes, it's perfectly okay. Now, when I have the position of a ray on the sensor, P prime, then I can use the intercept theorem to compute the position of the object. And let's do that in RayJack ONE. I have prepared a little script. No need to show all details. Let me simply run until this point. Run to cursor. And what you see here is a scene which is very simple. It's a screen and two circles at different distances. Then here you see symbolically the light source, and when I zoom in, you can recognize the lens, and this yellow thing here is a shield to prevent stray light, and finally here the sensor. Now let me go back to the script. This line is to make all light scattered from the objects colored orange. Now here we have the interesting part. We are using a so-called detector user distribution, which creates a two-dimensional distribution of something. And what something is, that's you have to define that. Now here it is attached to the sensor, and whenever a ray hits the sensor, it will invoke this function TOF, standing for time of flight. What happens is it takes the ray position on the sensor, it computes the distance as according to the formula I have shown you previously, and if the coordinates are permissible, it will simply set the pixel to this value. Here I have, as always, the ray tracer, and let me now, after ray tracing, simply show the distribution we have obtained. This should not take too long. And you see it's still a little bit noisy. Here you can watch here, you can read off the values. And when I hover here over the object, I can immediately read off the distances. Now let me go a step further and make a few changes. So I would like to look at another scene, use a little bit more rays, and use another detector. So this way, what I do is I simply toggle comments. So now the new detector is also a user-defined detector attached to the sensor. And if it is a ray hits the sensor, this function will be invoked, make cloud. Now cloud is an empty list in the beginning. When a ray hits the sensor, it computes first here the position of the ray in space. Once again, the distance of the object. And then here it uses this intercept theorem to compute the position on the object. Now, then it appends the result to the cloud. And finally, let me change here too. After ray tracing, these points form a point cloud. It's called point collection in RayJack ONE. And this is added to the display to the graphical view so that you see the reconstructed object. Let me run that, and it won't take very long. So here the object is now a gummy bear, and it takes a while until ray tracing is performed. And then, so you will see the black rays hitting the gummy bear, and the orange rays hitting finally the sensor. And now it's almost done. Give it another 2 or 3 seconds, and then the point cloud is reconstructed. So let me turn that around, remove the rays graphically, remove the object, remove all objects actually, and then you see the reconstructed point cloud. In principle, you could now fit an optical surface into this point cloud, but that's something which I will show in one of the upcoming videos. Thank you for your attention.